So the first part, or perhaps the whole of this lecture, will be devoted to a recap of what we've been doing so far. So we started by defining linear representations. In which the main character is a finite group. And then there's a V, which is a finite dimensional vector space over C. And the representation, a representation is a morphism, a linear representation of G. Is a morphism, a group morphism, a morphism of groups from, let's call it rho, from G to GLV, which is the group of invertible linear map from V to V, but also once we choose a basis, it's a group of invertible linear matrices. Yes, say if the dimension of V is n, of n by n, the invertible matrices. Then we defined the concept, the important concept of direct sum of representation, or representations. So if rho I from G to GLVI, so the group G is the same, but the VI are different, and so are this morphing for I from 1 to, let's say, T are representations. Then the direct sum of this representation is a representation of G denoted with this rho 1 direct sum, or rho T. So it's still a morphism from G to where, say, the direct product of this GLV, which leaves, which is a subgroup of the general linear group. I mean, this is called the general linear group. On the direct sum of the vector spaces. Okay, and what's this? Well, this takes G to what? Well, I need the tuple with of elements in each one, and of course the tuple is yes, okay, fine. Okay, so in other words, if I have this vector space V1 Vt, but I don't consider all the invertible matrices on it, but I only consider, well, let's use these things here. I only consider the matrices. All the squares are equal, but in general the dimension could be different. I think square, if I go here. So it's something like that, where here you have rho 1 of G, here we have rho 2 of G, and so on, okay? Rho T of G. Block matrices. Everything is 0 except on a block diagonal, okay? So each rho I acts on VI. So we don't have full matrices, but something like that. And why is this concept of a direct sum of representations? Because there is an important result due to Maschke's theorem, which tells you that any representation, so a linear representation, well, say, as a consequence of Maschke's theorem, is the direct sum of irreducible ones. And then, of course, I have to say what an irreducible representation is, and this is next. So rho from G to GLV is irreducible. I should probably say that all representations are on vector spaces different from 0. Okay, otherwise we don't consider them. So it's reducible if V is different from 0, and if the only rho G invariant subspaces of V are 0 and V itself, where rho G invariant means, so U, a subspace of V, is rho G invariant if U in U and G in G imply that if you apply rho of G to U, you're still in U, okay? So there's nothing between, it's in some sense a simple object. Like a simple group is a non-trivial group in which there are no normal subgroups except the trivial ones. Okay, so here the only rho G invariant subspaces are 0 and V. These are of course rho G invariant, but there aren't any other. Okay, so as a consequence of Maxwell's theorem, you can decompose its representation in a direct sum of irreducible ones. And so in a sense, studying the reducible ones is all you need, because then with this simple construction, say blockwise matrices, you can obtain all representations. Then we have defined the homomorphisms or morphisms of representations. Well, if you have two representations, rho I, where I is 1 or 2, then a morphism from rho 1 to rho 2 is a linear map. So a morphism in the category of vector spaces, F from V1 to V2, which respects the action of the rho I, such that, so this is a linear map to respect sums and multiplication by scalars, but then such that, you take, such that for G in G, rho 1 of G followed by F, this is a composition of maps, because rho 1 of G is a map on V1, so it goes from V1 to V1. So composition is left to right. This goes from V1 to V2. Okay, so in the end, this is a map from V1 to V2 equals this. Okay, and of course, this goes from V1 to V2, and rho 2 of G, by definition, goes from V2 to V2. Okay, so it's a map. So a morphism representation is a map that commutes, say, with the action of G. When we recall the idea of modules over the group algebra, this will become even more transparent. So this is a morphism, and of course an isomorphism of representations is a morphism which is an invertible map. Okay, so a morphism, invertible, as usual. And then in this case, you see that you don't really need both rho 1 and rho 2, because rho 2 of G, I mean, now if F is invertible, the case can be written as F1 inverse rho 1G F. In particular, if the two VI coincide, you see that here we are just doing a change of basis. Recall that a change of basis on a vector space has the effect on linear maps of conjugating with the matrix of a change of base. So let's write change of base or basis. Or you remember that I switch continuously from base to basis, but it's the same object. So if the VI are the same, this is a change of basis. Great. And this is a good point to recall the idea of CG modules. So we have introduced the group algebra, CG. I mean, we gave a formal definition of the group algebra, but informally, this is a vector space over C. All vector spaces are over C in this course, except when otherwise noted, with bases. You see these bases this time, the elements of G. So it's a vector space. So you have a sum and you have a multiplication by scalar. But then you want you also to turn into a ring, and which becomes also a ring, and actually an algebra. As we say, extended the multiplication on G linearly. Actually, I defined originally the group algebra via the convolution product, but informally, if you have two elements of the group algebra, so these are linear combinations like this. Okay, so the idea, what does mean extended multiplication linearly, which is exactly what a convolution does, means that you have a sum where G and H are on G, AG, BH, GH. And then if you collect all because this is not written in standard form, because these are written in standard form because the elements of G are a basis. So this is a linear combination of the basis element. Here, you will have the same element repeated, but if you write them in standard form, you'll find exactly, well, let's do it then. So the idea is that, let's use different letters then, that you have X in G, okay, and then you sum over, say, okay, X, AG, BH, say over GH, well, okay, let's say GH in G such that GH equal X, okay? So it's like polynomials, okay? Like polynomials. I mean, polynomials, you make sure that the indices sum to something, and here you make sure that the two indices have the product being X. So the two variables are redundant. You could use just one, but okay. So that's the group algebra. And so, I mean, I haven't defined correctly what an algebra is, but you should probably know the concept, and then it's given in the notes. But informally, is a ring, which is also vector space, and the two operations. For instance, the plus is the same, and so on. The two operations are somewhat compatible, and the group algebra has an important universal property. So suppose you have a representation, okay? So you have G going to GLV. So these are invertible matrices, okay? Informally, because I mean, this means they have, I have chosen a basis. And then this goes in the endomorphism ring algebra of V, which is just the ring or the algebra of matrices, of all matrices, okay? This composition, I mean, of course, here you have two operations. These are matrices, so you have sum and product. This composition becomes a morphism of monoids, because this is not a group with respect to multiplication, because there are non-invertible things, but it's a morphism of monoids, if you look just at a product. And then there is a natural map which sends G into CG. I mean, you simply, I mean, after all, CG as a basis, the element of G, so this is just the inclusion. And the universal property tells you that this yields an algebra morphism. Okay, so if you have a representation, you can extend it, and we'll say how it works, to C of G, and this become an algebra morphism. And this algebra morphism is exactly equivalent to, I mean, if you decode what the fact that this is an algebra morphism from CG to NV means, this is exactly equivalent to having a structure of a right, well, let's say right, but CG module on V. And so there are two equivalent languages. You can use the languages of representations, but with this, I'm not going into the details. You can also have you can also use the language of CG modules. Just to see what this algebra morphism does, so essentially, if V is in V, and say some G, and this is an element of the group algebra, then the module action, so the fact that V becomes a CG module means that there is an action of these elements of V that satisfies satisfies certain axioms, and the action is exactly the right action, but it's my choice. The idea is that that you I mean, the scalars, these are, of course, these are elements in C, act naturally on V, and then G, the elements G, act via rho. Okay, so that's where the representation enters. Okay, but as I said, using you see, in the language of module, you simply write V times this, in a sense, use disregard rho. It's the same dual approach we have with group actions on sets, in which you may define the group actions as certain maps, okay, and then you name the map, or you simply say how they act, okay, without giving a particular symbol for the action, although you can have different actions. And then there are why is this useful? Because, for instance, what is let's just stick to an isomorphism. So an isomorphism of representations becomes, in this language, an isomorphism of CG modules. That is, you have V1, V2, two CG modules. So imagine that something like this holds, except that once it holds with rho 1 and once with rho 2, and F from V1 to V2 is an invertible linear map. Such that for a sigma in CG, you have sigma F equal F sigma. So this time, if you compare with the previous definition, previously I had rho 1 of G and rho 2 of G, but in the language of CG modules, I mean, this is implicit. I mean, when I'm acting on V1, I'm using rho 1. When I'm acting on V2, I'm using rho 2. Okay, so you see that, in a sense, disregard for a moment the fact that it's invertible. This is a linear map, meaning that it commutes with scalars, with multiplication by scalars. I mean, respect the sum, and then you can pull scalars out of the map. Okay, so I mean, something like that if you have lambda in C, F is VF lambda. You can pull the scalar out. And what we are doing here, we are doing the same, but with the whole elements of CG. So V sigma F. I mean, this is an equality of maps. So of course means that if you take any V in V1, you will have this, okay? So it's like being linear, I mean, homogeneous actually, means pulling out lambda, and here you can pull out the lambda in C and in the complex numbers, and here you can pull out the element of CG, okay? And so you can, you have so an irreducible representation corresponds to a simple module, simple or irreducible module, a module which has no non-trivial submodules. I mean, in a sense, it's slightly more natural. It's a slightly more natural thing. Okay, so we have at least one problem with representations. That is, we may have different representations which, however, are isomorphic. Just quoted this, okay? And there is an idea due to Schur of introducing characters, which makes this much simpler. What does it mean? So if rho from G to GLV is a representation, linear representation, its character is the function chi from G to C given by, so chi of G for G in G is the trace of rho G. Note that I have never clearly distinguished whether GLV is just the group of invertible linear matrices or whether it's a group of matrices. Of course, as I said several times, I recall several times, it's a group of matrices once you choose a particular basis on it. But this is independent on the basis because changing a basis means conjugating the matrix, and then the trace, usually, as you know, is invariant under conjugation because the trace of a product AB is the same as the product BA. So this is independent of the basis, of the chosen basis. And for the same reason, a character, the characters of two isomorphic representations are the same. Okay, because two isomorphic representations are conjugate. Okay, which is useful. And we see that also the converse holds. So here we are saying if you have two isomorphic representations, then the characters are the same, okay? Because I mean, the two representations satisfy this. And so the two traces are the same, okay? But we see that also the converse holds. And this is very useful because the concept of being isomorphic between representations, which is somewhat intricate, becomes in terms of characters equality. So we will recall isomorphic representations. Let's put it in a different way. On the one hand, you have the concept of isomorphism of representations. So two representations could be different, but be isomorphic. We'll have example later. And this corresponds to equality of characters. And of course, believe me, it's much easier to deal with equality of functions in particular than to be dealing with isomorphism or representation. Because after all, isomorphism depending on knowing whether there is or not a map F, whereas equality, you just compare. You don't need to solve this equation, say, in a determinate F, okay? One more thing, I mean, this property of the trace of AB equals trace of BA, also means, note, that characters are class functions. When we say class, means conjugacy class. I mean, the standard term is class function, but means that they are functions of conjugacy classes. They are constant on conjugacy classes. of G. Why is it so? Well, recall the fact, I have an element G, and then I conjugate the element, okay? And I want to prove that this is the same at chi of G, where chi is a character, okay? So it's constant on a conjugate class. But the character is just the trace of rho of H inverse, and rho is a morphism. This is elementary, but I mean, I want to make sure that we are clear about that, okay? And here we see the property that the trace, if you have a trace, you can permute these elements and the trace won't change. And so this is chi of G as desired, okay? So class functions, okay? And independent of if you have two isomorphic representations, because of this, the characters are the same. But also the converse holds. Why? Because say, we can define, let's say, yes, if you have two functions, well, f1, f2 are two functions, well, okay, let's write it, are two functions from G to C. You can define a certain inner product. You define f1, f2, the inner product written as a pair, but it's really a product, which is an average. We can do it because we are on the complex number, so every non-zero element is invertible. Well, okay, say, okay. And then we take, what do we take here? We take f1 of G conjugate, f2 of G. Okay, this is clearly an inner product. I mean, it's linear in the second component, and what do you say, it's squilinear in the first, because you need to take a conjugate. And then there is this important thing that let chi I of G be the trace of rho I of G. Okay, where for I equal 1 of 2. Okay. Oh, yes, but I should say where rho 1, rho 2 are irreducible representations. And then we have we have proved using Schur's lemma, exploiting the Schur's lemma, which looks harmless, but then as we saw as a quite important consequences, we have proved the so-called orthogonality relations. And this tells you that if the two representations are isomorphic, then their inner product is 1. They are irreducible, okay? If they are not, then the scalar product, the inner product is 0, okay? So you see that we already saw that if you have two isomorphic representations, they have the same character. But if you have two non-isomorphic representations, they don't have the same character, because if they have the same character, the inner product should be 1, instead it's 0, okay? Because note, as a particular case, of course, if I have just one representation, this is 1, okay? So if the two are not isomorphic, the character have to be different, because if they are the same, the inner product should be 1. But if they are not isomorphic, the inner product is 0, so they are not the same, okay? So we have proved that distinct, that non-isomorphic representations correspond, or say the isomorphic representation correspond to same characters, which shows that the characters are an important simplification, okay? There's perhaps one thing that I should also mention, that, no, let me see whether this, no, this is not needed, I can do without. Great. So, let's go to the paper. So recall that we had recalled at the beginning of this lecture that you can decompose a representation in a direct sum of the reducible ones. Okay, so if a certain representation is the direct sum of certain representations, remember that this time I won't follow the lines. That this means that you have something like this. Okay. That rho of G is a blockwise matrix, 0 everywhere except here. And so, of course, we find that that if you take the trace is the sum of the elements on the diagonal. So the trace of rho G will be the trace of rho 1 of G plus the trace of rho 2 of G plus the trace of rho T of G, because I'm looking just at the diagonal. So if chi of G is the character associated to rho, and chi I of G is the character associated to rho I of G, then this implies that chi equals chi1 plus chi t, where of course this means that chi of G is chi1 of G plus and so on. Is the usual sum of functions from G, actually from the classes to C. I mean, you sum the values, okay? So the direct sum of characters correspond, of representation correspond to sum of characters. Here too you see the simplification, because this is the sum of functions from G to C, which is very simple. This is slightly more complicated blockwise matrix, but this is just a sum like this, okay? Now the question that, oh yes, and this is important, if each, no, wait a second. Well, okay, yes. Now suppose that, let's rewrite this in a different form. So suppose that n, that chi is equal to n1 chi1 plus n2 chi2 plus, let's use a different letter, ns chi s. So of course n1 where the ni are positive integers, okay? Where the chi are different. So what I have done, I have joined together the characters here that are the same, okay? N1 chi1 means, of course, chi1 plus chi1 n1 times. The usual multiple, okay? Then I'm wondering what is chi, okay? And remember the orthogonality relations. If the two are not isomorphic, the inner product is 0. Otherwise is 1, okay? And so what we get here, well, the inner product from this to this is 0, and the inner product with this, with itself, will be 1. And so this will be n1 squared plus n2 squared plus ns squared, okay? Because I distribute the inner product is distributive on both sides, and so all products from this to this are 0, because chi1 chi2 is 0, and if you have the product n1 chi1, well, disaster, n1 chi1 n1 chi1, you can pull this out. These are positive integers, so the conjugate is the same. So you take n1 squared chi1 chi1, and orthogonality relations tell you that this is 1, so you get n1 squared, okay? Why is this important? Because you can now define an irreducible character, because we know that an irreducible character has this property, that chi1, if chi1 is reducible, chi1 is 1, this inner product. But conversely, if this product is 1, this means that you have only one factor and it's 1, okay? Conversely, so if chi is 1, then chi is the character of an irreducible representation. Okay? Yes. So I should have said here where, okay, where the chi are characters of irreducible representations. So you see, we can recognize that chi is the character of an irreducible representation because I mean, if it is the character of an irreducible representation, is one. This inner product is one by the orthogonality relation. But if this is one, then chi has to, then of course the point is all ni have to be zero except from one, which is equal to one. So chi is the character of a irreducible representation. So as you see, you can recognize an irreducible representation from its character, okay? When this holds, when the inner product is one, exactly the elements that are that have this property, okay? Great. And then we had considered the problems. How many? Let me talk in this. Let me use this language. Irreducible characters are there for a group G. Why is this language convenient? Because otherwise I should have said that. I'll write this down. How many pairwise non-isomorphic irreducible representations? So instead of irreducible characters, I could have said pairwise non-isomorphic irreducible representation, which is longer and more involved, okay? But the point is that isomorphism for representation means equality for characters. So in a sense, I should add distinct, but this is, when we count elements, we don't count twice, okay? So distinct, in a sense, is included in the concept of how many, okay? So distinct corresponds to non-isomorphic, which is better, okay? We are equality and non-isomorphism to take care of. And yes, and then the idea is very simple. Well, posteriori, hindsight, as we say, is 2020. So if you consider the right regular representation, rho, which is the representation from G to GL, and let's say CG, because I need to put a vector space here. And this, recall, is a vector space that has as basis the element of G. And this is simply the map that sends G to what? To the map that sends H to HG, for where HG are in H. Of course, the image of G under rho has to be a linear map on this. And I just need to declare it on a basis and take a basis element. Recall the group algebra as basis element, the element of G. You multiply it on the right by G. And let psi be its character. And then we already discussed this. I mean, if you take an element G different from 1, then H is always different from HG, okay? Because H equals HG only when G is 1. And so the trace will be 0. Because, I mean, if you look, if G is different from 1, you take rho of G, and this sends H to HG, okay? And these two are different. So what does it mean that they are different? It means that this one is not on the diagonal, okay? Because the two indices are different, not on the diagonal. So the character, this property, psi of G is 0 when G is different from 1. Where, on the other hand, if G is 1, then of course you have the identity matrix. It is the dimension of this vector space is the order of G, you get the order of G, okay? So this is very simple character. There is only one value different from 0. But this is important. Why? Because I mean, we can say, we know from Maschke's theorem that this character will be the sum of these characters where the chi are distinct irreducible characters. Not all of them for the moment. We don't know that they are all of them. And the ni are, say, positive integers, okay? And then we want to know what's ni, okay? So if chi I is any irreducible, okay, let's say that these are greater than or equal to 0, are all the distinct. It could be infinitely many, but of course in this sum only a finite number can appear. If chi I is any irreducible character, okay, so on the other hand, on the one hand, psi chi I is ni, okay? Just the orthogonality relations, okay? You distribute, and the inner product chi I with the other chi j is 0. But then what's this? This is 1 over g, and then I have to do this, take the sum over, let's rewrite it. Note that I have to take a conjugate here, but really the conjugate doesn't play any role, because psi has real values, actually positive integers value 0, and the conjugate of 0, of course, is 0, and then the number of elements of G. And so there is only one factor which is different from 0, because all the values for G different from 1 are 0. And so we have just one factor is for G. When G equal 1, you have, on the one hand, the order of G, which is the value of psi of 1. And then you have chi I of 1. These two simplify and get chi I of 1. And this is the dimension of the underlying vector space, okay? Because it's the trace of the image of the identity matrix under, of 1, the identity of the group under rho I. Rho I is, of course, the underlying representation, and this is the identity matrix of size. I mean, of size, the dimension of Vi. So what we have found that if you take any reducible character, then this appears in this decomposition, and it appears exactly chi I of 1. This is called the degree of the character. Chi I of 1 times the dimension of Vi. So what we found that Vi is the sum from 1 to S of chi I of 1 chi I. So this is an integer, okay? A positive integer. Okay, and where these are all the irreducible characters, okay? Any irreducible character appears here, is one of these, and appears how many times as its degree, as the dimension of the underlying vector space, okay? So in particular, there is a finite number of irreducible characters. Okay? Because they all appear within psi, okay? So, and this is which is a finite dimension. There's another way of seeing this, because I have this, and I'll finish the lecture with this, and then I'll start tomorrow's lecture by recalling further where we were, and then we continue. And note this, I mean, you can evaluate this in 1, okay? So I'll rewrite this on the page. So this is the character of the right regular representation, and this is the sum. So this is a coefficient, okay, and this is the character. So when I evaluate this in 1, recall in 1, the value is order of G, what I get is Well, I get, sorry, 2s. Okay, so this is just the sum square. And another way of putting it is the sum of the squares of the dimensions of the underlying vector space, where rho I from G to GLVI are the distinct, the pairwise non-isomorphic irreducible representations. So there's a finite number of pairwise non-isomorphic irreducible representation, which means distinct characters, because of course this sum is finite, so only a finite number of terms can be different from 0. So we have recalled everything up to now, and we'll continue tomorrow, and then we will be proceeding further and starting computer character tables and the like. So that's all for today. Thanks, and see you tomorrow.